Hi, this is Maggie from Design Code Debug Repeat. Welcome to the channel. This is the 9th installment in the Adventures with Python series, in which we learn Python by building a text adventure game. No prior programming experience is needed, but you should watch the series videos in order. I'll link the playlist here and in the description. Let's get started. Right now, we've got a pretty complete version of our game, a basic foundation that could be enhanced and extended into a feature-filled text adventure game. But in the next few videos, we're going to tear it down and build it up again as an object-oriented system. Why? Because classes and objects are very powerful. Many modern languages have at least some object-oriented capabilities, and an object-oriented system can be easier to enhance and extend if it's designed well. Even if you end up preferring the non-object-oriented implementation, you might like to include some object-oriented components. You should at least have the option. Object-oriented design is a way of approaching a programming problem by assigning the responsibilities of the system to different objects. Each object represents something meaningful within the system and knows how to manage its own data and behavior. When the program runs, these objects interact in well-defined ways to solve the overall problem. In contrast, functional decomposition takes a top-down approach, breaking the system into smaller and smaller tasks that are implemented as functions. In this video, we're going to create an object related to our game and learn how to incorporate it into the game. With this knowledge, you can incorporate your own classes and objects into any system. In the next video, we'll create one or two other objects so you have more examples, and then we'll redesign the entire game as an object-oriented system. I'm hoping that the example in this video will make a lot of sense: an inventory class. An object is data encapsulated with operations on that data. Think about what an inventory is composed of, what data it should contain, and what operations you would like to have on an inventory. Use the inventories we have in our game already as a model. An inventory should be composed of items, whatever we decide items should be. In our current game, items are names and descriptions. You'd probably like to be able to start the inventory off with some initial contents. In our game, the player starts with an empty inventory, as do many of the locations, but other locations start with some inventory items. You'd like to be able to exchange items between inventories, such as when a player picks up or drops an item. We exchange the item between the location inventory and the player inventory. You'd like to be able to get a string representation of the inventory, as when we list the items in a room or the player examines their own inventory. We'd like to be able to examine an individual item, and we'd like to know if an item is in the inventory. It would be good to either know how many items are in the inventory, or at least if the inventory is empty. We don't use this functionality directly in our game right now, but it would be nice to be able to add an item to the inventory, and maybe delete an item from an inventory, independent of a direct exchange. Maybe an item is created, or is used up. What I have here is a UML class diagram representing the inventory class I just described. A class diagram is a kind of UML diagram. UML stands for Unified Modeling Language. It is a visual language, a standardized way to describe software using diagrams instead of code. There are many different UML diagrams, but the most common one you'll see is this one, the class diagram. This class diagram is broken into 4 rows. The first row you can see is the name of the class. Class names begin with an uppercase letter, and if they're composed of multiple words, each subsequent word is capitalized. This is the only time we write identifiers this way in Python, and it clearly communicates to other programmers when reading your code that the name represents a class. The 4th row is a description of the responsibilities of the class. This is sometimes omitted in class diagrams, but I will often write this row when I'm designing a class and I don't yet have the implementation worked out. It's basically a natural language description of the operations, like what we just discussed, so I won't repeat it. The 2nd and 3rd rows are implementation details. The 2nd row is for the data, called fields in object-oriented terminology. The 3rd row is for operations, called methods in object-oriented terminology. Fields and methods together are called class members. Our single field is called items, and I've chosen to represent that as a dictionary of name description pairs, just as we do in the current game. We may choose a different way to represent items in the future. Most classes will have more than one field. For example, we might want our inventory objects to have a name, like knapsack or treasure chest or puzzle box. And if that were the case, I'd also have a name field, a string. But let's stick to the simpler version for now. The third row is the methods or operations on the data. I've listed here all of the operations we discussed. Init is the method that will give our inventory a starting state. And then we have add, remove, examine, exchange item, contains, and str. Those last two begin and end with double underscores, as init does. In Python, these are sometimes called dunder methods for double underscore, and these are methods we won't invoke directly on our objects. These methods allow our class to work like a built-in data type. The str method is what's used if we want to print our object or convert it to a string, and the contains method is invoked if we use the in operator on an inventory object. So we are essentially defining a new data type in Python, and we can even write our data type so it works with some of the built-in operators like in, for, equals equals, and the other relational operators, which, if I'm honest, I think is incredibly cool. Another thing about the class diagram you might have noticed is the dash in front of the field and the plus signs in front of the method names. These symbols indicate visibility, what the program that creates an object of our class can do with that object. When designing a class, we decide on a public interface, the fields or methods that a program can use when working with our object, and we decide on a private implementation, the part of the object that remains hidden from programs that use it. A rule of thumb is to keep fields private, signified by a dash in a class diagram, and methods public, signified by the plus sign. There are several reasons for this, and it's more subtle than a simple field method private public split, but that heuristic will do for now. In Python, there is actually no way to enforce private visibility, as there is in many other languages, but naming a private member with an underscore as the first character of the name, as I have done with items, communicates to programmers using your class that they should treat the member as private. If they try to directly access or modify it, they do so at their own risk. Now let's look at the implementation. I've already implemented inventory, and I've also written some unit tests to test that the class works as expected. Let's start with the class definition. We start a class definition with class inventory : corresponding to the first row of our diagram. This opens a class definition in Python, and then all code that is part of the class is indented underneath. The second line of the class diagram is the class fields. In Python, the fields of an object come into existence when they're defined, when they appear to the left of an assignment statement, just as other variables do. We don't list them explicitly as part of the class definition, as is done in statically typed languages like Java and C++, for example. But it is good practice to list them in documentation. You can see in my docstring under the class header, I've written attributes, and then underscore items, its type, and a description. Below that, we have all of the methods. They are regular Python functions, except the parameter lists all begin with the parameter self. Within the methods, you'll notice if I reference the items field, I prepend it with self. What is self? Self is the inventory object the method is operating on. A program that uses this class can have as many inventory variables as it needs. We're defining a data type. Look down where the testing code is, and you can see I'm creating two inventory objects, inv1 and inv2. And below, notice I have the code inv1.add egg, a jewel-encrusted egg. That will invoke the add method. Which inventory object should egg be added to? Inv1, the object before .add. Inv1 will be passed automatically by Python as the self parameter to the method. When I write self._items, it's inv1's items field that we're modifying for this call. We always invoke methods this way. There are exceptions, but generally speaking, the name of the variable dot and then the method name. Python takes the object referenced by the variable and passes it as self. Methods will usually either change the object data or return some information about the object data, so methods are almost always working on some part of that self object. So looking at the methods, the init method is the one that's called when we create an inventory object. I do that twice below. Inv1 equals inventory, and then I pass in a dictionary of 3 name description pairs. And inv2 equals inventory, and I pass in nothing. This is how you create an object of your own data type. Variable name equals class name and then arguments matching the init parameter list in parentheses. This will invoke the init method. I've written the init method so the items parameter defaults to none if nothing is passed in. Inside the init, I set the items field to an empty dictionary if no argument was passed in, and otherwise I copy the dictionary that was passed in. So for inv1, its items field will be a copy of our dictionary of 3 name description pairs, and for inv2, after the init method has executed, its items field will be an empty dictionary. The diagrams you see to the right of the code are called object diagrams, and these are another kind of UML diagram. An object is an instantiated class, a variable of our user-defined type. Object diagrams show the name and class of the object in the first row, and then the fields and the values in the fields in the second row. You can draw an object diagram to represent the state of an object at any point during program execution. This is what inv1 and inv2 look like after the initializers have executed, after the lines inv1 equals inventory with the dictionary parameter and inv2 equals inventory open close parentheses. In our methods, we then have add, which takes a name and description as parameters along with self and returns nothing. This simply adds another name description pair to the self.items dictionary using the parameter values. The code is self._items sub item name equals item description. It's critical that we put self. In front of _items so that the name description pair gets added to the objects dictionary. It won't always cause an error if you don't, but it definitely won't have any impact on your object if you forget it. This method is meant to add an item to the inventory. If we don't write self._items, the object's inventory will not be changed. It's really easy to forget to put self. At the front of your object's fields, and it can be a difficult bug to debug if you forget it. Trust me, I've forgotten it many times. I speak from experience. Now, we also have remove, which returns true or false depending on whether the remove operation was successful. It takes the item name as a parameter and first checks if it's in self._items before popping it and returning true or false. The examine method checks if the parameter item name is in self.items and returns the description of the item if it is, and an empty string if it isn't. I made a decision here to return an empty string and not text like I don't see item name here, because any program using this class has the power to check if the item is in the inventory before trying to examine it. In our game, the main program is where the human-computer interface will be, so I'll let it decide how to interact with the player if they try to examine something they're not holding. You'll notice that none of these methods interact with the player in any way. There are no print or input statements. That's because this is a data type for a program to use. These methods modify the inventory or answer questions about the inventory for another part of the program. That's often hard for learners to get used to when they're learning object-oriented programming. But think about the dict data type, for example, or the list data type. They do not print or ask the user for input. They exist for a program to use. The exchange items method takes the name of the item to be exchanged and another inventory object. I had to put that annotation for the other inventory object in quotes because we're in the middle of the definition of inventory. It isn't fully defined yet, so we can't reference it yet. We'll be able to annotate using the class name inventory outside of the inventory class definition. The method checks if the item is in the object's items field, self._items, and if it is, it removes it from its own items and adds it to the other inventory using the add message. So here you can see we're calling the add method on the inventory object that was passed as a parameter, other inventory.add item name, value. We then have an isEmpty method, which will return true if there's nothing in the items field, if it's an empty dictionary, and false otherwise. Our two final methods are the dunder methods that give our class a little built-in capability. The __contains___ method will return true if the parameter passed, the name of the item, is contained within our inventory. We're simply going to return item name in self.items because we can use in with a dictionary. But this allows a programmer who creates an object of our inventory class to use in with our inventory class. And finally, we have an str method, which returns a string version of our inventory. If somebody creates an inventory object and casts it to a string, or prints it, this method will be invoked. I'm returning a string of indented item names, 1 to a line. Below my class definition, I have a main function which tests all of the methods. I've written the tests to print a separator and then a description of the test, followed by the expected and then actual result. I'm going to run this, and I'm going to show you the test case in the code, the output, and the object diagrams representing the two inventory objects after each test. Since inventory is now defined, we can annotate our two variables as being of type inventory, and we can create them. We do that by writing variable name equals and then the name of the class followed by the arguments to the initializer. We never pass the self argument explicitly. Python will do that. It will pass the inv1 object to the first inventory initializer, and it will pass the inv2 object to the second inventory initializer. Now, it's important to understand that the object doesn't exist until we've invoked the constructor. Just as with any variable in Python, annotating a variable doesn't cause it to exist. A variable doesn't exist until it's on the left side of an assignment operator. After we've created the inventory objects, we can send them messages. I start by printing the inventory with 3 items, and you can see the result of the __str___ method below that. Notice we're not directly invoking the dunder method str. We've written print inv1, and str is implicitly invoked. I then check if each inventory is empty by sending the isEmpty method. When I send the message to inv1 with 3 items, it returns false. When I send the message to inv2 with no items, it returns true. Then I add an egg to the inventory with inv1.add egg, a jewel-encrusted egg, and print it again. The add method doesn't return a result, so I just write the object name dot and then the method name add and pass the arguments in. Inv1, the object name before the dot, will be passed in as self, and after this executes, inv1's items field will have an additional value. We then exchange the book with the empty inventory and print the empty inventory, which now contains a book. This method returns true if successful and false otherwise, so I'm printing the result. And it looks like inv1.exchangeItem, so sending that message to inv1, so inv1 is self, and then I pass in the item name to be exchanged and the other inventory. I next exchange a non-existent object with the other inventory, and that returns false. It didn't work, as expected. There's no necklace in inv1. The next 2 tests are using the in operator, book in inv1 and egg in inv1. The book is no longer there, so that test returns false, and the egg is, so that test returns true. Note this invokes the dunder method contains. Okay, so we print inv1 again to confirm the book is gone. We then examine the egg. We send the examine message to inv1, which does contain an egg. We then examine ego, which is not an item in inv1, so it returns the empty string. We remove the egg from inv1, which returns true, and then we try to remove it again, which returns false, since it's no longer there. Now, this is a very useful way to write a class, to write it with a thorough set of tests in the file that will only run if we're executing this file. Remember, we ensure that the main method will execute only if the script is run, not imported, with if name equals main. I can import this class into my adventure game and the tests won't run, but I'll be able to make objects of the inventory type. If I make changes to inventory, I can run these tests again to make sure my class still works correctly, and if I add functionality, I can add tests. The trickiest part of adding the inventory class to our program is going to be in saving and restoring, because we can't directly save and restore an object of the inventory class. Right now, our dungeon is a data structure composed of ints, strings, lists, and dictionaries. All of these data types map directly to JSON data types, numbers, strings, arrays, and objects. So I'm going to begin by adding 2 methods to our inventory class, toJSON and fromJSON. The class will still work exactly as before. It will just have some additional functionality. The toJSON method will simply return the items field, because that's a dictionary, which is a JSON format. The fromJSON method will take a dictionary as a parameter and store it in the items field. I'll add some tests at the bottom too, 2 to test each method. I'll send inv1 the toJSON message, and I should get back a dictionary consisting of knife and its description, and nest and its description, because that's what's left in inv1 at this point. Let's also create a JSON of an empty inventory. I'll create an empty one and send it the toJSON message. We will expect that to produce an empty dictionary, open close curly brace. To test reading, I'm going to create a third inventory with some items in it, and then send it the from.json message with our knife and nest inventory. We expect that to now contain only knife and nest. And then I'll send it the from.json message again with an empty dictionary, and it should be empty. I'll print it after each message. And if we run that, we're getting the expected results from the to.json and from.json messages. So we know if we send to.json to our inventory object, it will return a dictionary which can be written directly to the JSON file. And if we send it from JSON, it will constitute itself from that JSON, regardless of what it might already contain. This class is in good shape now to add to our game. Let's incorporate the class into our dungeon now. This version of the program is called shabbyabby v9.py. And we will want to change this program so the player's inventory is now an inventory object and not a dictionary, and the inventory for each location is now an inventory object and not a dictionary. At the top, under my other imports, I'm going to write from inventory import inventory. This will import my class from the inventory.py file so I can use its name directly in this program. The first inventory, after from, is the name of the file without the .py extension. The second inventory is the name of the class in the file. We're going to need to change all parts of this program that use the inventory in any way. The getExits string function does not use the inventory, so that should be safe. Now, getDescription prints a description of the items in the location, which will now be stored as an inventory object. That means that location sub inventory, the value for that key in the location dictionary, is now an inventory object and not a dictionary. Instead of if location sub inventory, which was checking if the dictionary was empty, we'll have to send the isEmpty message to that inventory object. So if not location sub inventory dot isEmpty. That might feel weird because it's not a simple variable name before the dot. But the value at that key in the location dictionary is an inventory object. So location sub inventory references an inventory object, and we can send it any message defined in inventory. And remember that printing the inventory or casting it to a string will return an indented list of the inventory item names. Let's add UC to the description, and then we'll cast the inventory to a string, so description plus equals str in parentheses location sub inventory. The inventory swap method definitely works with inventories. We'll change the data type of each parameter to the inventory type. The exchange item method will return true or false, so we can write if from inventory.exchange item to inventory, and that will return true if the exchange is successful and false if it isn't. So if it's true, we can write print item has been action, period. And if it's false, we can write print I don't see item, period. Okay, the two JSON methods, saveAbby and loadAbby. We'll start with saveAbby. The parameter that comes in, called Abby, is really our data parameter. It's a dictionary composed of dungeon, player inventory, and current location. We'll need to convert player inventory from an inventory to a JSON format. That's pretty easy. We'll just write Abby subplayer inventory equals Abby subplayer inventory dot to JSON. So we'll replace what's there, an inventory object, with a JSON version. Now for our dungeon, we'll do the same thing, but we'll have to do it for every inventory in every location in the dungeon. So for location in Abby sub dungeon, location sub inventory equals location sub inventory dot to JSON. And let's annotate the variable location as a dictionary of string object. Now, to read that in, we'll do that in reverse. We'll produce something that contains inventory objects where the inventories are, but we'll be reading in dictionaries. Let's change the empty dictionary in our default dungeon to an inventory object. Then, after we've loaded the file into the variable Abby, again, that's really a data variable containing the three components we write out. We'll create an empty inventory and then send it the from JSON message, passing in Abby sub player inventory. And then we'll iterate through our Abby sub dungeon and do the same thing for location in Abby sub dungeon, create an inventory, send it the from JSON message, passing in location sub-inventory, and then setting location sub-inventory to the new inventory. And we'll annotate the inventory variable of type inventory and the location variable of type dict_str object. Now in main, where we're assigning Abby, location, and inventory after reading in data, we don't need to change the code because we're just pulling those pieces out of the data dictionary. The only thing we need to change is the annotation of player inventory to inventory. Going through the commands, moving isn't affected, and we've mostly taken care of saving and restoring. The only thing I want to do here is make a copy of the data structure before I pass it to save Abby, because I'm overwriting this data structure before I save. I'm converting the inventory objects to dictionaries. So I don't want to overwrite my actual inventories. I'm going to import copy at the top of this program and send copy.deepcopy data in instead of data. The look command won't change, but take, drop, inventory, and examine all relate to inventory. Take and drop both call inventory swap, which we already rewrote. If we check, we can see we're passing the correct parameters. Each inventory is already an inventory object. For inventory, we're using join with the inventory dictionary. That won't work. But we have isEmpty, and we can convert our inventory to a string. So we can write instead, if player inventory is empty, print you aren't carrying anything, else print you have, print player inventory. And for examine, we still want to check that the user typed the name of something they want to examine. Because we wrote the contains method, we can still write if command part sub1 in player inventory. The only thing we need to change is to send the examine command to player inventory, rather than getting the description from the value in the dictionary. So print player inventory dot examine command part sub1. Now, if we run the game, we can interact as before with our inventory and with the location inventories, and the program works. But why did we go to all of this trouble? It was a lot of work, and we don't seem to have gotten any benefit. In fact, writing out to the JSON file was more trouble than before. I chose the inventory object because it's always easier to imagine concrete objects as classes and objects in a program. If I had started with something more abstract, it may have been more difficult to grasp what an object is. But yes, basically we've written a wrapper around dictionary that doesn't even have all of the dictionary's functionality. One reason is that this is a step toward making the entire system object-oriented, which will have advantages. But the main reason is that the inventory class can be a lot more than just a wrapper around an existing data type. Here's an inventory implementation with additional features. I haven't tested this one, just threw those features in as an example, so I'll upload it to my GitHub repository, but don't expect it to work. This inventory has a lock feature. An inventory might get locked if a spell is put on it or an actual physical lock. An inventory can be locked and unlocked with the correct key, and no operations on a locked inventory work. The inventory also has a capacity, max items, and you cannot successfully add an item to an inventory if it's already holding its maximum. I changed add items to return a Boolean result so we can know, back where we try to add an item, whether it worked or not. I've also made sure we don't exchange an item if the other inventory can't accept it. We could also make the items themselves more interesting, such as including a class for each item, not just name and description, and then have the inventory broken into sections so it can show us all of the magical items, or all of the healing potions, or all of the clothes, all of the food, for example. Right now, our inventory just stores items, but because it's a class, we can give it any abilities we can imagine, like the ones I've described and shown you here. If we tried to add this functionality with a plain dictionary, we'd need many variables per inventory and functions distributed around the program to support this functionality. The advantage to having a class is the data and operations are encapsulated together into one object. Everything having to do with the inventory will be part of the inventory class definition. As the game grows, dividing it into objects will help us manage the increased complexity. So how can you practice with this before the next video? Take that monster dictionary I keep bugging you to write and turn it into a class. Then write a program that uses your monster class. Maybe they can fight each other in your game. When you're feeling confident with defining and using classes and objects, join me for the next installment of Adventures with Python. As always, have fun and keep coding.